When warning klaxons sound inside a spacecraft, the crew has seconds to stabilize the vehicle. Alarms flash, telemetry drops, and the margin between a successful abort and a catastrophic loss of crew shrinks to zero. A pilot bypasses panic and ignores the urge to improvise. They reach for a spiral-bound manual, trace a finger down a column of text, and flip a specific circuit breaker. This manual represents the physical execution of a risk response plan, a core element of PBOK. PBOK, or the Project Management Body of Knowledge, is the institutional standard for identifying and mitigating risks in high-complexity environments. Every go-no-go decision on the flight deck relies on what project managers call work performance data. That flip of a switch is the final physical output of years of institutional planning, testing, and forensic analysis of past failures. We are deconstructing this architecture of contingency to see how NASA translates abstract project management governance directly into split-second survival logic. We will trace this evolution from the qualitative risk acceptance of the Apollo era to the computational redundancy of the modern Orion spacecraft, and finally to a recent Artemis anomaly that tested the ultimate trade-off between quality, schedule, and scope. In deep space, the titanium and software of a vehicle are only as robust as the organizational framework that manages their limitations. To understand how an agency handles a crisis, we must look at how it establishes operational boundaries long before a rocket reaches the launch pad. At the top of the documentation hierarchy are the general rules, established by the Office of Manned Spaceflight. These act as the enterprise environmental factors and project charter. They dictate the high-level policy that governs every mission. Below that sits the Flight Mission Rules Document, or FMRD, serving as the project management plan for potential system failures. The foundation of this pyramid is the flight data file, the actual physical manuals stowed on the flight deck. These are the direct work instructions the astronauts execute during flight. Before a crew ever touches the real flight data file in orbit, every procedure undergoes man-in-the-loop simulations. Astronauts run through the steps in high-fidelity mock-ups under artificial stress, serving as the program's ultimate quality assurance gate. Consequently, when an oxygen tank fails or a computer faults, the crew does not improvise. Their physical actions are pre-authorized responses, driven by layers of institutional risk management logic. Executing these flight rules requires onboard hardware capable of processing complex telemetry. The baseline for this computing power was established in the 1960s. This chart shows the spacecraft flight computer evolution, starting with the red bars representing the Apollo guidance computer. Notice the extreme constraints: a total memory capacity of just 38 kilobytes and a processing speed of 0.043 MIPS. Because early lunar missions were relatively short, NASA accepted a total loss of this single computer as a qualitative risk. Modern deep space missions require strict quantitative risk mitigation. Looking at the blue bars for the modern Orion Flight Control Module, the system possesses 4 gigabytes of memory and operates at 2,000 MIPS. The bottom row illustrates the critical architectural difference. While Apollo relied on a single point of failure, Orion utilizes a quad hot and warm backup system, running 4 independent flight control modules simultaneously. These 4 computers do not operate in a voting architecture where they compare answers. Instead, each module independently calculates that it is flying the vehicle. A Power and Data Unit, or PDU, arbitrates their commands sequentially, prioritizing Computer 1, then 2, and so on. If Computer 1 experiences a critical fault, the system does not pause to troubleshoot the error. The PDU immediately ignores the failed unit and accepts the exact same command from Computer 2, maintaining continuous control. This design reflects a shift in aerospace project management. The agency no longer just accepts the risk of computer failure. They quantitatively mitigate the probability of that failure through redundant, independent networks built for deep space survival. When quality control testing identifies a severe nonconformance in flight hardware, project managers must navigate the iron triangle, the necessary trade-offs between a project's scope, schedule, and cost. Following the uncrewed Artemis I test flight, inspections revealed exactly this type of nonconformance. The Orion capsule's AVE-coat ablative heat shield suffered unexpected char liberation, with pieces of the material cracking and shedding off. This anomaly was tied to the capsule's skip entry trajectory. Returning from the moon, Orion dips into the upper atmosphere to bleed off speed, using aerodynamic lift to skip back out into space, and then plunges back in for its final descent to the ocean. During that brief dwell time outside the atmosphere, heating rates drop, but thermal energy continues accumulating inside the heat shield. Because the Avecoat material lacked permeability, the gases generated by this extreme heat could not vent. Internal pressure built up, expanding and ultimately fracturing the outer charred layer. This presented a textbook PMBOK dilemma. NASA could redesign the heat shield to ensure uniform permeability. However, that path required a massive expansion in project scope, extreme financial cost, and an indefinite schedule delay for the Artemis program. The alternative was to modify the re-entry trajectory itself to limit the heat shield's dwell time. This approach preserves the existing hardware, but pushes the mission schedule to April 2026 and significantly tightens the operational landing corridor. NASA chose the operational path. By altering the trajectory, they maintained the rigid quality baseline of crew survival and safety, while avoiding the infinite cost and schedule overruns of a complete hardware redesign. The rigor of this decision stands in sharp contrast to historical failures, where risk management broke down, most notably during the Space Shuttle Columbia disaster. In 2003, a large piece of insulation foam violently broke away from the shuttle's external tank during launch, striking and fatally damaging the thermal protection tiles on the left wing. The original engineering baseline for the space shuttle was explicit. The project requirements mandated that absolutely zero debris shall emanate from the external tank during ascent. Yet, over the course of 79 previous missions, foam strikes occurred repeatedly. Instead of halting launches to fix the root cause, the organizational culture drifted. Management slowly redefined foam shedding from a critical flight failure to an acceptable maintenance issue. Catastrophic loss rarely comes from a sudden, unpredictable hardware failure. It comes from the normalization of deviance, when an organization routinely bypasses its own quality assurance gates and slowly accepts abnormal risk as the standard operating procedure. As human spaceflight pushes outward to Mars, the architecture of contingency faces a severe physical limit. At Martian distances, communication delays with Earth can reach up to 40 minutes round trip. With a delay that long, Mission Control in Houston cannot issue real-time change requests. If a life support system fails, ground controllers cannot analyze the telemetry and read up step-by-step troubleshooting procedures. The entire contingency framework must evolve. The paper manual held in an astronaut's hand will be replaced by fully autonomous algorithms running directly on board the spacecraft. These systems must process millions of data points and independently decide when to abandon a primary mission scope and execute a secondary survival plan, entirely without human intervention. The computational hardware and physical design of these future ships will look nothing like the Apollo or Artemis capsules. But the underlying project management principles dictating their software, the strict definitions of risk, quality, and scope, will remain absolute. The survival of a deep space crew depends on the rigorous governance of risk, a commitment to baseline a response, and a total refusal to normalize a deviation from safety.